Okay, guys, we're in our next unit here, which is thermochemistry. Here's our video one for this. Here we go. So first thing in this video we need to make sure we do is we need to talk about energy and make sure that we have a good understanding of what energy is. So our basic definition of energy is the ability to do work or cause change. Now in the chemistry world, we're usually talking about chemical energy, which is able to do some sort of chemical reaction or there's some sort of movement of energy or heat within our reactions. So the unit for energy is the joule. Okay. Sometimes we associate energy with calories in our country, but the common unit that we use here is the joule. To give you an idea of what a joule is the energy it takes to produce 1 watt. You guys are probably familiar with watts, with like light bulbs, that kind of stuff. 1 watt of energy for 1 second. Okay, so if you actually had a 1 watt light bulb and you lit it up for 1 second, that was a joule. Okay, now that's an extremely small amount of energy when we talk about joules. To give you a little comparison, if you took a single green pea, delicious green peas, and we had one of them, they have about 1,000 joules of energy in it. Okay, and that's about 1/4 of a food calorie, which is not a lot of energy at all, really, in our world. To give you one more comparison, there's 4.18 joules in a calorie. Now, the calorie we're talking about here isn't calories in terms of food calories. When we talk about food calories, you'll notice how anytime you see that, they actually capitalize the C. And it's kind of a shorthand notation to say that this is not actual calories, but it's actually more of a kilocalorie. Okay, so in the food industry, when they talk about, this candy bar has 273 calories, it's actually 273,000 calories in the scientific world. Okay, so this kind of gives you an idea of what energy is, and the unit that we're going to be using throughout this whole unit is the joule. Okay. So first thing we want to do is, what is heat versus temperature? Okay, we use those two terms a lot, and a lot of times people think they're the same thing. Okay, so throughout the unit, you're going to see a new word associated with heat, and that's called enthalpy. All right, so heat and enthalpy really are the exact same thing. It's just a fancy word for heat. In the scientific world, we call it enthalpy. Okay, so when we talk about heat or enthalpy, we're talking about the total energy within a system. Okay, we're not necessarily saying it's hot. We're just saying that what is the amount of thermal energy in this system. Okay, so you can have things that are very cold, but if you have a lot of stuff there, it still contains a lot of energy. Okay, you can also have things that are very, very hot with very, very little stuff there that also contains lots of energy. So it really is a comparison to the temperature and how much of the substance you're looking at, or what is your sample size. Now, temperature really doesn't care about your sample size. All it measures is the average kinetic energy of our system. Okay, so heat is total energy there, and temperature measures the average of the particles inside there. Okay, so if we do a comparison, and we say which of these two things is hotter. Okay, so we have the Atlantic Ocean, that is 50 degrees Fahrenheit, and we have a hot tub, which is about 102 degrees Fahrenheit. Okay, so the first question should not be challenging. So which one is hotter? Obviously, the hot tub is hotter. It has a higher temperature. Okay. But if we say which of these two bodies of water has more enthalpy or more heat to it, okay, even though the Atlantic Ocean is much cooler, because it's such a large body of water, it contains way more heat energy that's available to use. Okay, so the hot tub actually has more temperature, but does not have more heat energy. Okay, we use the oceans to basically regulate our entire planet in terms of heat sinks and heat dumps because of how big that body of water is. It can absorb lots of energy and then transmit lots of energy back and forth on a daily cycle, which allows us to have pretty moderate temperatures throughout our planet. We sometimes don't think that in Minnesota. That's primarily because we're not close to a very big body of water. You get close to big bodies of water, your temperature is always going to be more temperate because the water helps regulate that energy because it has so much available energy. All right, so let's talk a little bit more about enthalpy. Enthalpy, if we want to define it, is the heat content of a system. So as we go through any chemical process and some physical process also that we have, you're going to see a change in enthalpy or a change in heat as we go forward. Now, when we symbolize that, for that change in heat, we use a delta H. Okay, so delta H is a change in H. H is enthalpy, so we have a change in enthalpy. Okay, as we go through this unit, we're going to hit changes in enthalpy in lots of different areas. So for melting, for freezing, for boiling, for condensing, for chemical reactions, for dissolving into solution, and for standardized formations of actual substances. Okay. Now these aren't all the places that you can see enthalpy changes, but these are the places that we're going to kind of study it as we go through this unit. Okay. So just be aware that anytime I use the word enthalpy, I'm really talking about heat energy, and it is symbolized with this delta H. Now, as we go through this unit, we also need to make sure that we're really comfortable with this idea of endothermic versus exothermic, okay? And we already know that endothermic means energy being in, okay? So some things that are new to us that we want to make sure we put down and keep track of. First of all, is when you have energy going in, our change in energy is always going to be a positive value. So note that or highlight that, because we're going to have negative values too. And when we talk about the math we're going to be doing in this unit, we got to make sure that anytime energy goes into a system, we call that being positive, okay? We also need to make sure we know the difference between surroundings and our system, okay? So when you're dealing with endothermic and exothermic, you have to look at the system, not the surroundings, because the surroundings are going to be doing kind of the opposite of what the system is doing, okay? So if the system is taking energy in, the surroundings has to be releasing it to that. It might be forced to do it, but it has to be doing that. If the system is releasing energy, the surroundings has to be absorbing that, okay? So often, sometimes students get mixed up and they think of endothermic and exothermic based off the surroundings, and you really shouldn't. You should be based off your system. Now, the system can be really anything. The system can be a chemical reaction. The system can be a chunk of metal. The system could be a pot of water. The system could be the entire Atlantic Ocean we could talk about. The system could be our whole planet if we really want to. It's whatever the focus is of our research or our study or what we're using in terms of that problem we're dealing with, okay? So sometimes you get this question, okay? So is endothermic things always cold to us? And the answer to that question is actually absolutely not, okay? So we are a warm-bodied person, and we have a certain temperature that we maintain all the time. So when we touch things, if it feels hot or feels cold, is actually a function of whether or not if it's warmer or colder than our hand is itself. It doesn't mean that what's going on in that process or that system is actually endothermic or exothermic. Okay? Now, it is true that when we feel things that are cold, that often leads us to this idea of being endothermic, but it's not necessarily always true. So we got to be kind of careful about that as we go through this unit. What we really should be looking at is a change in temperature of the system. So did it start off cold and get warm, or did it start off warm and get cold itself? So looking just at the system, not our hands or what we're touching, because our hands or what we're touching would always be a surrounding. It's not really the system itself. So let's do kind of an example here, something that might be, we know what's going on, but we maybe haven't talked about it in this light before. So which of these two things is endothermic, okay? Freezing something or melting something, okay? We talked about that in a previous unit, when we freeze things or we melt things. And let's kind of go through the thought process here. So if we're going to freeze something, okay, that means we're going from a liquid state to a solid state. So if you go from a liquid to a solid state, is that substance, let's just call it water, for freezing water, is that water absorbing energy to go to a solid, or is it releasing energy to go to a solid? Okay? Now flip it around. If you're melting something and you are going from a solid state to a liquid state, are you absorbing energy to make that happen, or do you have to release energy to make that happen? So hopefully in your mind you're saying, well, when you melt something, you are going from a solid to a liquid, so that means you must be absorbing some energy to make that happen, right? Because we got to break those intermolecular forces. So when you freeze something, you must be going from liquid to a solid, which means you must be releasing some energy, right? Which sounds kind of weird that when you actually freeze something, you actually release energy. So in terms of the endothermic process here, it's melting. Okay, so when you melt things, we are going from solid to liquid, which means you need to absorb energy to make that substance happen. So melting is endothermic, which means that freezing, which sounds really weird to us, but freezing is actually exothermic. Okay. Now again, sometimes that feels weird to us because we always refer back to our own personal experiences, and when we touch something that's freezing cold, like a block of ice, we feel it feels cold to us. But if you think about it for a second, when we touch ice, we're not freezing the ice. We're actually melting the ice, right? Because our hand is hotter than the ice. So when we touch it, we're actually causing melting to happen on the ice. And if the system is our ice, we're actually causing ice to melt, which is endothermic, okay? So that's kind of the first one. Now, if we flip it all around, we obviously get exothermic. So exothermic is energy out. So let's make sure that we're comfortable again. Anytime we take and we release energy from our system, we better make that a negative sign. So we have energy that's negative. And again, the answer to that is no. Every time we have something exothermic, does not feel hot to the touch for us, okay? And if we actually do a comparison here again, which of these is exothermic, boiling or condensing? Okay, so when you boil something, you're going from liquid to gas. So you're breaking intermolecular forces. So to do that, you need to absorb energy. So boiling here would be endothermic. And when you condense something, going from gas down to liquid, in this case, you are able to release some energy, which allows it to go from its gaseous state down into its liquid state. So condensing is exothermic, where boiling is endothermic. Okay, so these are some things that we probably should make a note of so we know which one is which. So boiling, in this case, is our endothermic process, and condensing is our exothermic process. Again, that may seem weird, like, wait a minute, boiling, things that are boil, that's endothermic? How's that possible? It would burn my hand if you're boiling water. True, but I tell you this, don't try this, but if you had boiling hot water and you stuck your hand in there, it actually would stop boiling for a second, because your hand, okay, would start to warm up because it's hot in that, so it actually would start pulling energy from your hand, so you would stop the boiling process by putting your hand in there. Okay, a better example of that would be take pasta. If you've ever made pasta or mac and cheese, as soon as you dump the noodles in, if you have boiling water, it stops boiling for a little bit. Okay, because all that energy now goes into starting to warm up those noodles instead of actually the boiling process. Okay, so give you an idea how that kind of works. All right, so we have endothermic and okay, guys, in this video segment, we're going to start talking about chemical potential energy and how it relates back to our chemical reactions. Okay, so first of all, we know what energy is. This is ability to do work or cause change. So when we talk about chemical potential energy, we're talking about that potential within the chemical bonds to make some changes. Okay, so all chemical bonds contain some sort of energy in them. It's what allows us to hold the molecule or hold the ionic compound together. Okay, so that energy is stored in this chemical structure of the substance. Okay, that stored energy we call potential energy. It has the potential to do something. Now, when we want to break a chemical bond, okay, it's kind of like breaking a board in karate. Okay, so when you want to break a chemical bond, you always need to put energy in. Now, once you have that bond broken, okay, and you start to make new bonds, there's always a release in energy, because forming chemical bonds creates stability, and when you're more stable, that's a reduction of energy. So they actually can release energy. So for every chemical reaction, we have this kind of two-step process. We put energy in to break bonds, and then we let energy back out to build new ones. Okay. The mathematical difference between how much energy it takes to break them versus how much energy we get when we build the new ones tells us whether or not this reaction overall is going to absorb or release energy. Okay. Now, in this natural world, the goal is to get to a lower energy state. Okay, so the lower your energy state you are, the more stable you are, and essentially that's the natural thing for molecules and atoms to do, is they always move towards lower energy, more stability is what they're trying to do. Okay, so we tend to have things that try to reduce our overall energy. So let's take a look at a kind of a graph on how that works. So here's some energy diagrams. Okay, so over here we have hydrogen and oxygen. Hydrogen and oxygen, they are going to react with each other. So here's the energy level that they sit at. This is their potential energy. Okay, they're sitting right here. Now, to get them to break the H2 and the O2 bonds, because they have to break these bonds in here, we need to put some energy in. So we notice how the potential energy goes up. Okay, the amount this energy goes up is called the energy of activation. So it's the energy it takes to activate this process. Okay, so all reactions have a little hump that we have to get over top of. All right, now once we've gotten over top of the hump, okay, then we start to build new bonds. So once we broke all these, we start to build the water molecules together. Now when you build the water molecules, that reduces your energy. Okay, so as a result, we have energy going in, and then we have energy coming back out. So our net change here is a negative energy change. So circle that or identify that as a negative energy change. So when we have a negative energy change overall, that means we have released energy, right? We started with more, we went down to less. So we've released energy. So when we release energy, this process would be exothermic. Okay, now that would make sense, right? If we can explode hydrogen and oxygen, we know that that releases a lot of heat energy to our environment. So the system releases all this energy to the environment, which is usually the air, the surroundings, whatever pan it's in, that kind of stuff. Okay, so this is our first example. So this is an example of an exothermic graph showing that process. If you flip it now, okay, so if we do the reverse reaction, notice how this is a reversible reaction. So now if we actually start with water and we reverse and go back towards oxygen and hydrogen, so the water molecule, again, you have to give it a certain amount of energy to get it to break those bonds. That's your activation energy. And then it releases it to make hydrogen and oxygen, which it actually can do. We can do that through a process called electrolysis of water. And our net energy change here is positive. So anytime we have a positive net energy change, we get an endothermic process. Okay, so we end up having it takes more energy to break these bonds to put in than we get back out. Okay, so in this case, the reaction can happen. It's not as likely to happen, but we can make it happen if we have a source of energy to put in. Okay, and we get an endothermic process here instead. Okay, so we have exothermic and endothermic. There's always a hump. There's always a starting point and an ending point. It just depends on which one starts higher, which one starts lower in terms of what's exothermic and what's endothermic. So this one here is a endothermic. All right. Now that leads us into this idea of thermochemical equations. Okay, so as we do chemical reactions, we need to kind of work on this idea of thermochemical equations. So we're going to stop the video here, and the next segment we'll talk about thermochemical equations. Thank you.